Well, so to get started, does everybody turn in their exam? Let me check to make sure. I think everybody's usually pretty good. All right, well, I'll just make sure. I want to make sure that you have the pledge signed. So, I want to briefly introduce. We have two guests today who are going to be staring at me along with you guys. We have John Ralston and Phil Haywood from X2 Biosystems. I'm working with them on a collaborative research project with athletics. John Ralston is the CEO of X2 Biosystems, and Phil works on their medical advisory board. In addition, he also works with the Seattle Children's Hospital as an athletic trainer for youth. So part of this research project is we're going to be aiding in concussion collection data and data mining research, security, and reliability. And hopefully, if we can get things working properly, we can actually take that and use that towards high school students, so we can actually help ensure the safety and reliability of these chips, so we can actually help make these sports safe at that level. So anyway, I enjoy working with them, and they've been kind enough to come down, and we'll be meeting with a number of people. But in this time, they're, I guess, while they we're learning about power and static and dynamic power consumption. So before we start the new material, does anybody have any questions about anything we covered in Section 4 so far? So in the previous lecture, we briefly covered, I'll scroll back to the beginning, basic power consumption equations, average power. We talked about energy, particularly power stored in a capacitor, and it's very important because, especially as we go into wiring and crosstalk, capacitors is when you have any two plates and you have some sort of potential between them. So dealing with the capacitors, we know that we are able to represent, we can simulate RC delay as a simple way of doing it without having to go into too much complicated simulation. We did a proof about, we were able to prove that the energy is proportional to the capacitance and the square of the supply voltage, specifically CL/VDD squared for energy. And then we were able to relate the static and dynamic power consumption. We figured out the switching factor. So we have the dynamic power is equal to switching factor times the load capacitance times VDD squared times the frequency, which is what we've proved here. Activity factor is important because we need to know how often the specific logic will switch in any given moment. So we have to differentiate between static and dynamic power consumption. Dynamic power consumption is what happens when you switch from a 0 to 1 or a 1 to a 0. And static power consumption is when the logic is being held at any given moment. We used a basic example here where we have some random switch where we have, remember, it's from 0 to 1. And the reason why we define it as 0 to 1 is because the clock has a 0 to 1 and 1 to a 0. So in order for one clock signal to occur, it has to rise again. So that's why we specifically defined it in that manner. So that's why we divide by half. That's why we divide by half here in this particular problem. Then we discussed these waveforms and how this is a switching of inverter. Now that I actually have my handy dandy, so we have a switch from 1 to a 0. We're able to relate this to the current. We were in saturation region for the PMOS transistor, and then we hit linear region and it goes back down. The reason why we're concerned about static and dynamic power consumption is when we're switching, a significant portion of this power consumption occurs during the switching. So we have our output, which is slightly degraded. So we have an input going from 1 to 0, and this is an inverter, so it's kind of falling along 0 to 1. And then we were able to ultimately relate it to the energy consumed in the circuit and the power consumed by the PMOS and the NMOS transistors. Then we worked on this problem where we actually figured out the switching power consumption based on we have a certain number of transistors in the computer chip. Here we have 50 million, which are logic, and then out of 1 billion, the remainder were memory. And we were able to determine based on the switching factors and the size, the lambda sizes, that we were able to actually calculate the capacitances of those circuits. and then ultimately using the switching, our switching factor, we switch 0.1, which means it takes 10 clock cycles on average to switch from a 0 to a 1. And then we calculated that the logic circuits calculated 27 nanofarads. And then the memory switched 2 times every 100 clock cycles. And that was 171 nanofarads because there's significantly more memory items in the chip. The supply voltage for both of them was 1.0 volts as defined in the problem. And we ultimately came up with 6.1 watts. Additionally, we're synthesizing a random chip. We are able to take this switching factor again and being able to figure out this with the size of the chip. Here we have 70 millimeters squared times capacitance per unit area. And then we have our switching factor again, 0.9 volts squared. And then we're able to figure out the supply voltage. Now, we also calculated switching probabilities. And this is important because this allows us to take it back to not only switching probabilities, but being able to calculate activity factors and ultimately power consumption. So we did this problem where we have 2 NAND gates and a AND gate with 2 inputs. They're negated. We are able to use De Morgan's law to take that down to a 2-input NOR gate on the end. Using those probabilities, we're actually able to calculate the switching factor, which was 3/16. And from there, we were able to calculate the actual activity factor, and that activity factor directly relates to the power consumption. Now, remember, somebody said, oh, this just got real because we got 15 over 256. But if we have a 4-input logic gate like we have here, you have 256 possible switches from like 0, 0 to 0, 1 or 0, 0 to 1, 0. There's 256 possible combinations, input combinations, of which 15 of them will result in a 0 to a 1 switch. And that makes sense because you would lay it out. There's only one instance, all ones, where you'll get that one output. And that makes sense also because 1 over 16, there's only one instance of the 16 possible output combinations that will give you that logic of 1 on the output. So that's that switching factor. And that actually, because of the fact that it goes from a 0 to a 1, and that's the switch, that's dynamic power consumption, being able to calculate this will actually help you design better chips. We also briefly went over clock gating. And the whole idea of clock gating is you have some sort of enable logic, a control, and here you actually have what you're trying to calculate. So you have a clock, and based on the enable logic, you ultimately want to have both of these as a 1, so then you can have your gate. Once they're both 1, then you will actually power the chip. The reason why is because if you recall you have a basic inverter, and your inputs and outputs, right? So ultimately what we're trying to do is try to control the supply voltage to a circuit. If you're not consuming power, if you don't have that supply voltage, because remember VDD squared has a portion to do with that. Ultimately, you're just completely cutting off that portion of the circuit, and the only power that's consumed is in your clock gating circuit. So the goal of clock gating is to significantly reduce power consumption. And then I showed you an example of these 64-bit Cokestone adders where they're actually having a trade-off in delay but reducing the gate sizes. So you have a circuit that's running slightly slower, but because they've significantly reduced gate size and they've re-optimized it, they were able to save 55% in power consumption. Then we went over some people are doing some really interesting things. They take the video game Minecraft and they're actually building computers and circuits in there. So they're able to kind of just look around in there and see what people are kind of doing for fun. And ultimately, we talked about this concept of voltage domain. Voltage domain, we're trying to minimize since power is quadratic with the supply voltage, the ultimate goal is to just have the minimum amount of supply voltage that will actually properly get your circuit where you go from 0 to 1 and you're able to get into your noise margins properly. However, you'd want to drive a higher supply voltage domain with a lower supply voltage domain, not the other way around. And the reason why is you might not be able to reach your threshold voltages on your transistors, and therefore you wouldn't be able to properly get that switch, as I'm sure all of you probably described on your take-home exam, and then the circuit would fail. So then we talked about what happens if this is unavoidable. We discussed this domain converter, level converter, where you can guarantee you have your input voltages, you have your high domain and your low domain. The low domain is driving an inverter, and based on the logic, you'll be guaranteed to get the proper voltage driving the next logic, so therefore you can actually properly operate the circuit. And the last thing we talked about last lecture was dynamic voltage scaling. So since we know that power dynamic is the switching factor times the load capacitance, frequency, and VDD squared, the two things that we can fix, that we can try to regulate in real time, are the frequency and the supply voltage. So we have our dynamic voltage scale. It controls both the frequency and our voltage. The switching voltage regulator will supply the supply voltage to our core logic, which is the circuit we're trying to operate. And the goal is to have the minimum sufficient frequency and supply voltage to complete the task. And the last two things we talked about, we're talking about static power consumption, and we're talking about this concept of sub-threshold current. That is using the current when the transistor is off, and it's directly relates to the body effect coefficient. And also we talked about stack effect, which negates this sub-threshold current because you have two transistors that are cut off and makes it significantly harder to have a current flow through these circuits. So the first thing we're going to be, that's new, example 4.5, is an example question where we are given two NMOS transistors in series, and they're tied to VDD. Now, what is the issue with tying VDD to an NMOS transistor? We just have some sort of VX on output. What's the issue?
Passes a weak one.
Passes a weak one. That's exactly right. So NMOS transistors are designed to pass things from ground to the output. We want to pass a strong zero. We have an instance where we have zeros on the NMOS transistors also. So these transistors are off. They should be cut off. However, we have some sort of sub-threshold current. So the drain of N2 is still at VDD, so the stack will leak. So it's going to have a small leak here. However, the middle node, Vx, settles to a point that each transistor has the same current. Now, because of the fact that we have two transistors, if you recall from the general idea of the transistor, we have our source, gate, and drain, right? And cutoff means that we are not able to create a full channel through the transistor. So if you have two transistors next to each other, you have the source and drain connected again, and you have a second cutoff, that's going to make it much more difficult for sub-threshold current, which is current we don't want, to get to the output. So using the equation we went over last class, we actually combine the two transistors, and since currents add in series, we have transistor 1 and transistor 2. It's the same current. What we're going to do is we're going to set the two equations equal to each other and then solve. So the sub-threshold current, we use the equation from topical objective, COT objective 4.14. The off current is equal to 10 times the Dibble coefficient, and Vx, which is our voltage between the two transistors, minus the supply voltage over S. That is equal to the current going through the N1 transistor, which happens to be the other transistor, and this is equal to negative Vx plus the Dibble coefficient, VDD minus Vx, so we've reduced the amount of voltage here. That's the difference between VDD minus Vx goes to ground, minus VDD, because we put that into our equation again, minus the body effect, minus V source base, which happens to be Vx. Now, solving this, I want to emphasize what happens when you actually solve it. We know that Vx is going to be equal to the Dibble coefficient times the supply voltage for 1 plus 2 times Dibble plus the body effect, and that's from solving this equation. The reason I'm having you do this is because I want to reinforce 3 concepts. One, I want to reinforce that the current through both transistors is the same. When you're working this problem, I really want you to understand that you're taking these voltages, so this is the second concept, adding voltages in series, and how that adds up, and that there's a body effect coefficient. That body effect coefficient ties into why we're having subthreshold current in the first place. And Dibble, drain-induced barrier lowering. So by using this portion, we end up having the subthreshold current is equal to our I off, or off current, times 10 to the negative Dibble, which is Dibble there, VDD. When you solve this, you're going to get 1 plus N over body effect over 1 plus 2N plus body effect. That does solve out if you because if you take these two and you start subtracting them and you cancel off I off, and then you do take the natural log of 10 and start solving for these, you're going to get Dibble, but you're going to have everything 1 over this denominator plus, it's going to come out over this denominator plus 1 over this denominator. That's how it's going to work out. This isn't a math course, so I don't expect you to, this isn't going to be something I'm going to ask on an exam, but I do want you to understand why this is going to work. This approximately comes to our Dibble coefficient times the supply voltage over S. So and this is coming significantly down, especially when you compare this value and this value. So the difference is, by adding this second Vx, you're actually reducing the amount of current, as opposed to now you have drain source current back up here, TGO 4.14. You're getting rid of this gate source voltage, getting rid of this drain source voltage, and you're significantly reducing the source base voltage. So by putting them in series and getting this stack effect, you're significantly reducing your stack effect. And ultimately, in stack effect, so this is another reason why NAND gates work better than NOR gates. Because with NOR gates, you're putting these PMOS transistors in series where you have much larger lambdas, and then the smaller lambdas are in parallel. Whereas in NAND gates, you have your PMOS in parallel, but you have these NMOS transistors in series, and you're able to take a much better advantage of this stack effect. So does anybody have any questions about this before I move on to gate leakage? Okay. So topical guide objective 4.16, we define gate leakage as occurring when carriers tunnel through a thin gate dielectric when a voltage is applied across the gate. So up to this point, we've kind of talked about, we have this leakage from source to drain, and we have this dielectric and a gate here. Gate leakage is what happens when we actually have current going through the gate. We shouldn't have that, which is why it's called a gate. So it's a strong function of the thickness of the oxide and the gate source voltage. It's an order of magnitude less for PMOS than NMOS, which is another benefit of using NAND gates. As we see when we get a little later in the course and we start synthesizing, NAND gates will be a strong decider for the circuits that we choose. You kind of had a little bit of an allusion to it already when you did your take-home exam. There's particularly the problem about somebody has designed that improper NOR gate or improper NAND gate, and the reason why is because they had the NMOS transistors in the pull-up network and the PMOS transistors in the pull-down network. The NAND gates in NOR are also addition with parasitic delay as well as logical effort. All of these kind of go into why NAND gates will be, NAND logic will ultimately win out. So ultimately, you're going to control your leakage in circuits by limiting the VDD. What do you think a drawback of that would be, though? Oh, good combining concepts type question. Why would controlling the supply voltage or regulating the supply voltage to try to get rid of this control leakage? I mean, ultimately, power consumption goes down quadratically with supply voltage, right? So you'd think that that would be especially if we're getting leakage problems and affects Dibble and affects mobility degradation. Why do you think that ultimately you have to keep it a certain height? What are some issues, do you think?
We're talking about threshold voltages.
You have to worry about threshold voltage. You actually have to create the channel in the transistor, right? What are some other things?
Maybe channeling modulation.
Mm-hmm.
Yes.
That is correct. I had one other thing. If you guys don't think about it, I'll just say it. One of the issues that we're having with implementing graphene is because you have to have some sort of logic 1 and some sort of logic 0, right? And they have to be and we learn noise margin. We have to be able to create some sort of change we're able to get from that logic 0 to a logic 1. Graphene's switching is there's not much difference. So they have to combine graphene with other silicon technologies to try to create this difference between 0 and 1. Ultimately, digital logic, we have to tell the difference. So ultimately, the smaller and smaller you make VDD in the same transistor size, it becomes more and more difficult to actually differentiate those. Now, one of the benefits is when you start getting, as you've been starting to see, we are getting lower and lower. We're currently at 22 nanometer, and Intel's starting to do 14 nanometer transistors. As the size gets smaller, you're able to have typically have a smaller supply voltage. But then we come across other issues like DIBL and gate leakage. Does anybody have any questions about that? All right, so this is this problem here. We're basically going to be we're going to be combining concepts. So a lot of the same numbers from the previous problem, but we're going to be combining subthreshold leakage and trying to figure out the static power consumption from that. So the problem reads, a digital system on chip in a 1.0 volt, 65 nanometer process. So what does this 65 nanometer process mean? What's this size relate to?
Feature size.
The feature size. So in particular, when we're drawing a stick diagram, which one of those is it?
It's like, isn't the length of my drains
With, yeah, poly, right? With 50 nanometer channel lengths and lambda of 25 nanometers. So lambda is your poly, it's going to be half of your feature size. Has 1 billion transistors, same thing, 50 million are logic and the remainder in memory. The average logic transistor is 12 lambda, and same switching factor is 0.02 and 0.1. Subthreshold for off devices is 100 nanometers per micrometer. So it's current per unit area. Current per length for low threshold devices, and 10 nanometers per micron for high threshold devices. Gate leakage is also 5 nanoamperes per micrometer. Junction leakage is negligible in this particular problem, which means later on we'll be dealing with those kind of issues in simulation, but for this problem, it means you can assume it's not an issue. Memories use low leakage devices everywhere. Why do you think that is? Bingo. It's kind of it's an exhibit, yo dog. I heard you don't like losing memory, so I'm going to make sure you don't lose memory kind of thing. The more you're losing leakage, you're losing information. If you're losing information, ultimately you're losing your data. So in memory devices, SRAM, DRAM, which we'll be learning about in the next section, low leakage device is very important because you want to save your information.
Don't they have like refresh?
Mm-hmm. Yeah, DRAMs in particular, you have to worry a lot about constantly refreshing. So DRAM, you have to every clock cycle you have a signal and you have some sort of loop back and it's a sequential element, and you're going to be refreshing it. So logic uses low leakage devices in all but 5% of the paths that are most critical for performance. So we've made a performance leakage trade-off in this particular problem. Now we're going to estimate the static power consumption. So first, we have our logic, right? So this is 50 million, and we've multiplied it by our lambda. And we know that 0.25 micrometers per lambda. And additionally, all but 5%. So we've calculated our width of those, of all of the chips in that particular area for our critical for performance. So for high, we have our 50 million times 12 lambda times 95% plus, and this also, the reason why we're also adding memory is because it's also a low leakage device. We have 1 billion minus 50 million times 4 lambda. Now again, we're multiplying by 0.25 micrometers because that is our half of our feature size. Right there. And then this becomes the total width of all of our low leakage devices. So at this point, we have a random, so basically the whole point of this problem is we have a random chip and we have a certain amount of logic and the rest of it's memory. And of that logic, we have some sort of calculation that we've done with high performance. For those of you going back to computer architecture and advanced digital systems, Amdahl's law would have been a huge huge factor in that kind of calculation. So now we are going to take these equations that we used before to figure out our actual subthreshold current. So here we have our width, and we're going to multiply that. We've calculated the actual width here. Our subthreshold current is 100 nanoamperes per micrometer, and 10 nanoamperes per micrometer for high threshold devices. So here we have calculated our low and our high, right? So we're going to add these together and divide it by 2. That becomes our average. From here, we then plug in the numbers that we calculated from before, right? Again, and from here, this number, our 100 nanometers per micron area, is the subthreshold for off devices. So we're taking our calculated low value and multiplying it by that particular current. So we have current per length, and then we're multiplying it by the length. And next, we have the length of our high threshold devices, and we're multiplying it by the current per length there. So now we actually know kind of the unit subthreshold current for the entire area of this 1 billion transistor chip. And so from here, we're going to take our width low and our high width, which we've calculated before, and we'll multiply that by 5 nanoamperes, which are gate leakage current. So here, since we're calculating gate leakage current for the entire chip, we're adding the area, the low, area of the high, the width of the low, width of the high. We're multiplying it by the current per unit per micrometer. So now we have the length, micrometers, the width per micrometers times the current per width. And then we solve that out to 275 milliamperes. And so, taking that back to a power consumption, which is ultimately what our problem wanted to do, we asked to estimate the static power consumption. P static, as we defined earlier, is equal to the static current times the supply voltage. And so we have our subthreshold and our gate current multiplied by 1 volt, which ends up being 859 milliwatts. So the whole idea of this particular problem, is that we have some sort of transistor chip, and some of it's doing logic, some of it's doing memory, and we want to calculate this subthreshold static power consumption. And what this means is we have these switching factors of 0.1 and 0.02, right? So when it's not switching, meaning we don't have a switch, we're consuming some sort of power consumption here while it's constantly high or constantly low. And based on our knowledge of the particular widths, our knowledge of what happens for high and low leakage, our knowledge of our trade-off in performance versus power consumption, we're able to calculate that actual static power. Does that make sense? Awesome. All right, so to kind of illustrate this a little further, I have included an example of a 3-input Nand gate. It benefits from the stack effect even further. So we have this supply voltage, and recall we have 1, 2, 3 PMOS transistors in parallel. That all goes to the output. And then we have, for the stack effect, we have 1, 2, 3 NAND gates of NMOS transistors in series. So we're really getting this stack effect here. So this is a good example. We're going to be going comparing subthreshold current and total current and how this actually applies for a 100 nanometer process. So in particular, I've described an example here where we're switching from 001 to 100. So we're actually switching 2 transistors, right? 2 of these 3 transistors. Actually, I can just go down here because I'm describing this circuit. So when we have the case from 001 and we're switching it to 100, we're actually switching the inputs on 2 of the transistors, but not getting a change on the output. So this is a worst case scenario for switching power, right? So what can happen is you only have, so if we have 1 and 0, what happens is we know that 1, if we have a 1 on this NMOS transistor here, right, it's now on, so we're passing some sort of current, and we also have subthreshold current on these 2 NMOS transistors below. So ultimately, what we want to do is we want to take advantage of the stack effect because we don't want this current flowing out here because we don't have a logic 0 yet. The only time we get a logic 0 from here is when we want 1, 1, 1. So here we had 0, 0, 1, so this transistor was on, and then we switched to an instance where this transistor is on. So that's our worst case scenario. So that's where the stack effect really comes into play. And so for this particular example, which is also given in the textbook, we have a 100 nanometer process for a 3-input NAND gate. We've defined the gate current as 6.3 nanoamperes. The PMOS gate is 0. And the off for NMOS is 5.63, and the off for PMOS is 9.3 nanoamperes. So we're going from 0, 0, 0 all the way to 1, 1, 1. And so when we have 0, 0, 0, we have all 3 of these are 0, so we have the stack effect. So Vx and Vz are the 2 voltages in between. So we have 0, 0, 1. Vx is cut off because of the stack effect, but we also have to worry about the supply voltage minus the threshold voltage for Vz. For 0, 1, 0, what happens is the middle transistor is on. So now we have to worry about this. So here we define these as intermediate because we have actual gate, some sort of gate current here, and we also have an on transistor here. So this transistor is what's keeping it from actually putting a 0, driving a 0 to the output. So we define these as intermediate. For 0, 1, 1, 0, 1, 1, this is the only transistor that's currently off. So taking advantage of the stack effect, these 2 transistors are on, so you have a current being driven to this transistor, and this transistor has to dissipate the power in order to ensure that, because at this point, if we have 0, 0, 1, we still have 0, 0, 1, right? So we have 2 PMOS transistors that are on that allow the supply voltage to put a 1 on the output. So this transistor is saving us from flawed operation. So in this case, both of them, both Vx and Vz, are going to be VDD minus VT. For a 1, 0, 0, I mean, it kind of follows from here. Vx is going to be 0 anytime our A, B, and C is 1. So A is 1 here. Now we have current flow, right? That explains why all of our voltages here are 0, because this allows our voltage 0. So if you're thinking, you can think of this as a gate. So the NMOS allows a 1 on it. When it's a 1, it can open, and it will allow a 0 through the output, which is why all of these instances where A is 1 is going to have a Vx equal to 0. So then our VZ, where N2 is off, is going to be VDD minus VT. That's your threshold voltage. Again, I'm sorry, that's stack effect. That makes more sense. So when this one is on, that means we have 1 and 1 for 1, 1, 0. This transistor's on, it allows 0 to go through. This transistor's on, allows 0 to go through. So now it's both of these are going to be 0. And this becomes VDD minus VT here. And then finally for 1, 1, 1, let me get rid of that. For 1, 1, 1, we have this instance where all 3 NMOS transistors are on, all 3 PMOS transistors are off. So therefore, we are able to supply 0 to the output. And the reason why both of these are 0, this is, if we were to do this, you would have VDD over minus VT for Y. And then this output would be 0 for this column, if we were to extend that a step further. So the reason why NMOS is because these are in parallel, so you're not taking advantage of that stack effect to be able to hold the 0 out. And if you're not able to hold the 0 out as well, what ends up happening is on NOR gates, they have a much harder time getting to the pulling up to 1, which is why their logical effort's higher. So if we recall, the logical effort for NAND gate is number of inputs plus 2 over 3. Whereas for NOR gate, it's 2n plus 1 over 3. So this is why the logical effort is significantly higher, because you're not being able to take advantage of that stack effect as much. So that's also another reason why NAND gates are chosen over NOR gates. So does anybody have any questions about this before I continue? So I want to talk about this concept of power gating. So up until this point, we've talked briefly about clock gating, but we also want to try to cut off the portions of the circuit that we're not using. So for example, in this previous problem, we had these 50 million transistors, right? And they're all being powered by the supply voltage. And they also had 1 billion minus 50 million memory transistors. And they're, in that particular example, they're all being powered by the supply. Now, since we know that supply voltage is a quadratic relationship with the actual power consumption, we want to try to cut down on the number of circuits within a chip that actually have the supply voltage going to it. If it's not being used, don't power it. So going back to the MIPS data path, if we're doing an R-type instruction, right? So we're using instruction memory, we're accessing the registers, we're going to the arithmetic logic unit, and then we're storing it back to the registers, right? We don't want to worry about jump, branch, all that other stuff. Cut off, just have enough voltage going to the memory to store the memory that's currently being held in the data memory. So this particular concept of power gating, which we're actually going to be, we have a bunch of PMOS transistors, and they're all powered by this sleep input. So in order to allow the 1 to go there, we'd have to have a 0, right? So if it's 1, that means we are in fact sleeping the circuit. We're not power gating the block. And so then we have this negated value with sleep and the output. So if sleep is 0, what that means is this gets negated and this output is 1. So that means we allow the outputs to go through. So I've also listed some issues with the power gating approach. The header switch requires careful sizing. It's important to, and what I mean by the header switch are these PMOS transistors above here. They require careful sizing, and we also want to have minimal delay. So once we need the circuit, it should be able to get the supply voltage as fast as possible. So because of the fact, and so now we're learning a little bit more about switching and sizing. So now we know that this activity factor applies to the capacitance. This transition between active and sleep modes takes time and energy because we have some sort of switch. We have to make it go fast in order to supply it. And additionally, if you don't have enough width, you can't cut off the supply voltage because these run in parallel. So power gating is effective in instances where you know that you can cut off the circuit for a certain number of cycles. So this is why for MIPS data path there's something called multi-cycle, which I talked about in section 1 really briefly, where we have this finite state machine where we know that certain power is going to certain portions of the chip, and we have other portions of the chip which don't have the power and we don't have the control signals. So when you're able to turn off a block long enough, like for a cycle or 2 or 3, then it's effective. But if the chip is going to be constantly accessed during a particular clock cycle, then it's not effective, and you're actually wasting more power. So now we're actually going to design one of these header switches. So we have a 65 nanometer process, noticing a theme here. A 65 nanometer process with a 1 volt power supply. Suppose the PMOS transistor has an on resistance of 2.5 kilo ohm micrometers. The block is being gated has an on current of 100 milliamps. How wide must the header transistor be to cause less than a 2% increase in delay? So in order for so we get some sort of input, right? So on your exam, you calculated your longest delay, your critical path. But in order for that critical path to occur, you're also guaranteeing some sort of supply voltage. So what happens is you calculated 160 nanoseconds for your delay, but we don't want to add 1.02, and this 1.02 comes from you get an input, then you have to wait for the supply voltage to get there, and then your circuit operates. So that's what we're calculating here. And so your customer has said, let's say your customer is X2 Biosystems. And they have said, in order to meet this power constraint, and power is a really big issue, especially when you're having chips that are going to be right next to the athlete or in the mouthpiece. It has to be able to keep working throughout the course of a game. It has to run on low power. So, but we're also communicating through a Bluetooth or wireless to the sideline, so that way your athletic trainer can actually see in real time whether or not somebody has a concussion or not. So one big thing is it has to consume less power, but delay is important. You want to be able to get that information as quickly as possible. So they have said that we don't want to, if it's greater than 2% increase in delay, this causes a problem for us because of wireless protocols. So this is your constraint. So to ensure a less than 2% increase, the virtual supply voltage should drop by less than 2% of the supply voltage. And we have 2% of 1 volt is 20 millivolts. And we have also defined our on current to be 100 milliamperes. So we calculate the effective resistance of our header switch by using Ohm's law. We know 20 millivolts, and we know 100 milliamps, so it comes out to 0.2 ohms. So then we're going to use that value and tie it back into our RC delay. Since the resistance width is 2 kilo ohms per micrometer, 2 kilo ohm micrometers, we just divide that value by the effective resistance. So this becomes 2,500 ohms over micrometers, and we divide that by 0.2 ohms. And those are going to cancel out. And the width of the block must be 12.5 millimeters. So what we've done in this problem is we have stated we can't have a less than 2% increase in the delay. So we have to reach that supply voltage. Therefore, in order to do that, the switching that occurs in the power gating circuit must reach that in a certain amount of time. Therefore, 2% delay means that it's 2% lower on the voltage than what we want. So what we've done is we multiply 2% times 1 volt, we get 20 millivolts. Now we have 20 millivolts, and we know our on current. So it has to not only have the supply voltage, the circuit has to turn on. So in order for it to turn on, we have to have some effective resistance where we have 100 milliamperes and 20 millivolts, so we've divided those, and we get 0.2 ohms. In the problem, we also know that our on resistance for the PMOS transistors, which we use for the power gating, are 2.5 kilo ohms times micrometers. So multiplying that out, our width is going to be kilo ohms times micrometers divided by our effective resistance, and that's when we get our width. So this is the width that it needs to be, going back up here, of these PMOS transistors in order to meet this design constraint. Does that make sense? Let a couple people finish writing up, and then we'll go to a combining concept. So, low power architectures. So now we're designing these chips. We've designed we've made these compromises between width, capacitance. We've worried about transistor sizing. We've worried about delay. We know frequency. Now we're going to start trying to putting these together into actually taking these cell blocks and building an actual computer architecture that does something. So building complex, sprawling processors to extract the last bit of instruction-level parallelism from a problem is highly inefficient use of energy. So if you recall from the previous course, instruction-level parallelism, you're trying to take advantage of these pipelining. So you have multiple stages. So in MIPS, there's 5 stages. So we have instruction fetch on an instruction while we're loading data memory on the instruction that's 5 before, right? This becomes inefficient if you keep trying to cut it down into different stages. So 5 stages is typically the most efficient if looking at from a power consumption. This is why MIPS was chosen that way. However, if you start adding 20, adding 30, it becomes more inefficient. So this is where parallelisms come into play. Memories have much lower power density because their activity factors are significantly lower. So what we're doing here is if we have 2 parallel processors running simultaneously, you can actually cut the frequency down by 2. If you're doing the same task, then you can cut it in half and get it done in the same amount of time with half the frequency. And since we know that this dynamic power is directly proportional to frequency, you get a trade-off in half of power with a half of area. So then you just go back, you go to your customer, and if they're willing to make that trade-off in area versus power consumption, then you can go with that. So we've talked about pipeline here. I kind of briefly alluded to it. And so there's this concept that's a little outside the course called super scaling and super pipelining, where you try to trade off the number of pipes that you want to have running a program versus the number of stages. And the trade-off is accessing area, cache coherency. So when you have multiple stages and multiple data paths, what ends up happening is you have these memories that you're trying to access, and you have to make sure not only they're not switching very often, but you have to make sure that the value of the data is accurate. So if we have 2 different pieces of data in 2 different data paths, you have value of X being operated here and here, and this data path switches it, what's going to end up happening is you have to ensure that this data path gets that value. So that's going to slow down the efficiency of your circuit. So the trade-off in power becomes reduced because the frequency is going to be a little lower. So you have the same amount of area, but a slightly lower frequency. So there's trade-offs there for each of those. But the big benefit, especially when you're cutting it down in half versus gaining half the area, is you significantly reduced your power consumption. The other big thing, so we've up to this point we've worried a lot about transistor sizing and transistor widths. Well, we've alluded a little bit to these wires that kind of go between each circuit, right? So when we drew, so you'd say you drew a 2-input NAND gate, and you have your VDD, your ground, you have your P diffusion, you have your N diffusion, right? And then you have your poly A and B. And then what ends up happening is you have your output, and then for your N diffusion, it goes out here, right? So we have poly, and this is our transistor widths are here and here. And our transistor length is here. But then we have these interconnects, right? These interconnects are going to be going from cell to cell. And if let's say you have two wires running close to each other like this, right? So in our design rules, we have a certain amount of width, right? The reason why is you have a charge carrier and a charge carrier and a width. So what is this? What do you have between your wires?
Magnetic field.
Well, it will create a magnetic field, but specifically you have one charge carrier and you have another charge carrier, and they're separated by a width. What does that create? It creates capacitance, right? So all of these, you start getting these wires closer together, especially as feature size goes down, you start having to worry about capacitance. So then interconnects, just the definition of interconnects, are the wires linking the transistors together. And they play because of the fact that you start creating these capacitance, and we know that capacitance is directly related to power consumption, it now has a very large impact on power consumption in circuits. Before, the transistors were slow and wires were cheap because you didn't really have to worry about them very much. But now as the transistors are getting smaller and smaller and everything's getting more compact, we have to worry more and more about being able to connect them. A call from the beginning of the course when we talked about Jack Kilby and the tyranny of numbers before we invented the integrated circuit. They believed that you had to connect every single part of the whole computer, which is why computers are so huge. And then he figured out, oh, okay, well, if you just do logic and you can properly ensure that the signal is getting to the other one, the other part of the chip, then you don't have to connect everything. But as these transistors get smaller and smaller, and they start dissipating heat, they start dissipating energy, and you start getting more and more capacitance as these wires are getting closer together, the wires become a much larger driver of power consumption in the circuits. So this particular aspect of capacitance between two transistors is known as crosstalk. And so there's an instance where you have two signals going through wires, right? And then what happens if they both switch simultaneously, or they switch simultaneously so they start going in opposite directions, or they don't switch at all? And between those different switches, we're going to be learning that has an impact on the power consumption of the circuit, particularly energy dissipation. When you have energy dissipation, if you're not worried about it too much, and you get heat going over to the next wire, you can actually change the logic of that wire. So you've actually have a circuit that no longer can be guaranteed to be properly accurate. So what ends up happening is we have to worry about the width of the transistor, the space between them, and the thickness of the transistor. I'm sorry, of the wire. So we have the dielectric height. The dielectric is what the wires are running along. You have the thickness of the wire, you have the length of your wire, and your width. And the space is you have to have a certain amount of space in between them in order to ensure that you're don't have this capacitive coupling or crosstalk. So the other important, this aspect ratio, which is the thickness over the width. And this becomes a very important concern. As your wires are getting smaller and smaller, your aspect ratios also impact power consumption. And we'll go into a couple example problems that describe that phenomena. And last, pitch is just the width plus the space. So this is kind of it. We have at the very beginning of the course, I talked about you have metal 1 and the stick diagrams you've drawn. There's only one metal. You have VDD, ground, and your output. When we started getting down to 0.6 micrometers for the process technology, you had metal 1, which is just for all of your transistors, but then you had to have metal 2 for vertical routing. So let's say you had a circuit up here, use metal 2, and then metal 3 was specifically for horizontal. And so then, since you're able to do that on different layers, and I'll show a picture here in a moment of how you're able to do that using dielectric, they could route between cells. But as your transistors are getting smaller and smaller and smaller, and you have to route more, and you have to worry about this capacitive coupling and crosstalk, you're going to have more and more layers. So your mid-layer one, again, it's going to be for routing within the cell, but your mid-layers are starting to get thicker and wider, and you're going to use your supply voltage, ground, and your clock signal for your thickest wires, because you want to maintain those signals. So your thickest wires, you're going to have for VDD, for within the transistor, you're trying to make them as small as possible. And this picture here is a comparison. Let's see if I can, yep, oh, sweet. All right, so this is a comparison of your stack from your Intel 90 nanometer process technology and your 45 nanometer process technology. So in the 90 nanometer stack, your transistors are all the way down here, and they had 6 metals. So these metal 1s are the ones that are connecting your cells just in between. You're actually connecting within the transistor. And metal 6, all the way up here, this is where your supply voltage and your ground and your clock signals are going to be. So in order to communicate between the different stages, you have to have, in order to account properly for horizontal, vertical spacing, you end up having 6 different metal layers. Once we get down to the 45 nanometer technology, now you're actually dealing with your metal, your transistors are just here. This is where a transistor is. So then you have metal 1, and they're already up to metal 8. So this is where your VDD and ground are. And all of these different metal layers, excuse me, all of that is worrying about connecting cells and interconnects within the circuit. And the reason why you have to have different widths and different heights, you have your dielectric here, you have your thickness and your width. So this is where your aspect ratio comes into play. And then the length is how far do you have to go to connect different cells. Now, if I remember, maybe 2 or 3 lectures ago, I told you that one of the biggest issues that CMOS designers have is they'll design some part of the circuit, and they'll design another part of the circuit, and they wonder why it doesn't meet the power constraint, because there's just this long metal 1 wire. Or they'll use this, they'll use a very thin metal 1 here, and it consumes a lot of power, and they're wondering why. Put them together, have a shorter wire, it'll consume significantly less power. And so I kind of have a description of your, you remember your pitch is your distance times plus the width of the circuit, and you have your thickness. So you can see that these kind of go down. These are nanometers and 7 micrometers. So this is 10 to the 9, and these are, so this is 7,000, kind of to put it in perspective with comparison to the rest of these. And you can see the width and the slack of the wires gets smaller and smaller as you get down to your lower metals. So the question becomes, how do we actually model these interconnects? So we learned earlier about this concept of Elmore delay. So we have we were modeling NMOS, so we had some sort of resistance, and we had capacitance going to ground. And then and we have our next resistor, right? So if we were modeling to a NAND gate, this would be our output, right? And so it was R1 times C1 plus R1 plus R2 and C2 and so forth. Recall that. So the whole idea is, how do we actually use this to actually model wires? So we have models. We know that we have some sort of capacitance between wires going next to each other. In addition, we know that it has some sort of resistance in the wire. So there's 3 different ways, and we're going to specifically focus on one because it's the most efficient way of modeling, called pi delay modeling. So the L delay model, it's just the way it's described is how it looks. L model is resistance and capacitor shaped like an L. Pi modeling, what it does is it actually splits the capacitance in half and has it on each side of the resistor. And then the T model is splitting the resistor in half and having capacitance in the middle. Now, through experiment, it was determined that the pi delay model is actually significantly more accurate. And in fact, you'd have to break the L delay model into 100 segments for the same accuracy as one pi delay model. And so I already talked about the Elmore delay here. So basically, we're going to be kind of going through resistance and sheet resistance. Then we're going to do an example problem where we're combining the resistance and sheet resistance of the wire with this capacitance and crosstalk to be able to actually determine how much power is being consumed by these interconnects. So we define the resistance of the wire of a uniform slab of conducting metal can be expressed as the resistivity of the wire times the thickness of the wire. So this is resistivity divided by the thickness times the length divided by the width. And the sheet resistance is a measure of the resistance of the thin films that are normally uniform in thickness. And recall that the wire was on top of your dielectric, right? And we worried about the dielectric. So that is this portion of your resistivity divided by the thickness of the wire. Sorry, the thickness of the dielectric. So you have your length, you have your width, and you have your dielectric underneath. And as we saw from the previous picture, those dielectrics become important because that's the difference between metal wires next to each other. So we're going to have wires on top and below each other, and then wires next to each other. And that's regulating that distance allows us to regulate power consumption in the circuit. And so what we're going to do is we're going to use this resistance equation. I'm going to go past the definition for resistance and have sheet resistance at the top. So we have 2 wires. One is thickness T, length W, and width, length L and width W. And then we have a wire that is twice the length and twice the width. And simply put, the resistance of the left, they have the same resistivity, they have the same thickness, and L over W, so that's the resistance equation. By plugging this in, we get 2L and 2W. Well, the 2's cancel out, right? So that means that these 2 wires have the same resistance. So let me reread the question for you and then go over the proof again. Example question 4.7, given 2 wires shown below with equivalent resistivity. So in that problem, the equivalent resistivity is here. Determine which wire has the greater resistance and prove this using the resistance equation. So you're given the resistance equation in 4.21. And by plugging that in there, we know that the length is twice as much as, and the width is twice as much as this circuit on the left, right? So this is just a simple concept question to understand that doubling the width of the wire and doubling the length of the wire will give you equivalent resistance. And so I wanted to include this table because this is something that will be helpful in the future problems. Until 180 nanometer a generation, so now we're up to 90 nanometers, and Intel is now running 22 nanometer, and they're doing research in 14 nanometer, right? So until 180 nanometers, most wires were aluminum. But then, as we started getting to this point, we had to start worrying about resistivity and power consumption as the wires mattered more in the power. We had to worry more about specific resistivity. So aluminum is 2.8 microohms per centimeter. So this resistivity matters per length, right? And then gold, copper, and silver. So copper atoms were diffused into silver atoms, but the problem is they kind of they don't play nice with FET sometimes, field effect transistors. So you have a diffusion barrier in between them in order to ensure that you can properly regulate operation of the transistor. So there's trade-offs. Aluminum has a slightly higher resistivity. Copper has a lower resistivity, so ideally it's perfect. However, good design requires good compromise seems to be a recurring theme over and over again, right? So, for 4.8, we are going to compute the sheet resistance. So recall, for sheet resistance is going to be resistivity or thickness, right? And then we're going to calculate the hole resistance if the wire is this length and this width. So the problem states compute the sheet resistance of a 0.7 micrometer thick copper wire in a 65 nanometer process. And the resistivity of copper is going to be 1.7. Find the total resistance of the wires 1.25 micrometers wide and 1 millimeter long. So we have a 1 millimeter long wire, which I'm obviously going much more than 1 millimeter. But we have ignore R right, that's copy and paste. But same equation, resistivity divided by the thickness times the length over the width. And we have 1.7 times 10 to the negative 8 ohms times meters, right? And that comes from 0.17 micrometers. And then that's our resistivity of copper. Now, this would allow you to calculate your sheet resistance, this portion here. Next, to calculate the full resistance, we count for a width and length of the wire. So then you get 1,000 micrometers, which is 1 millimeter, or 0.125 micrometers, and that becomes 800 ohms. Make sense? Okay, Warren. So the last thing we'll cover, since we're talking about pi delay models, is an Elmore delay. We talked about resistance. Now we're going to discuss capacitance of the wire. So we know that our classic parallel capacitance, we have the oxide constant, dielectric constant for oxide, and then we have the Planck's constant times the width and the length, right? And then if increasing area increases capacitance, right? You've answered that correctly on the exam. Increasing distance decreases capacitance, and we know our dielectric constants for air it's 8.85 times 10 to the negative 14 farads per centimeters, and to have that for our oxide, for our silicon dioxide, it's 3.9, so that's the multiplying factor. Now these are equations that are presented in the textbook. Most of these are determined through experiment. I'm not going to expect them to be TGOs, but they're good for you to kind of learn and understand. So you have a wire, and you have different layers, and you have some sort of capacitance between the wire below, the wire to the right, the wire to the left, and the wire above, right? So we're relating this to the actual capacitance. So this was 90 nanometers. This equation for the capacitance was equal to the oxide coefficient, width and height, and these are numbers that are determined in experiment. So you can see as you're adding wires, the key detail here is you have some sort of capacitance, and then again switching CL VDD squared, switching factor times frequency. So the more capacitance you have, the more power consumption you have to worry about. Again, this is another one. So here, this is the important equation, because we're going to relate this eventually to switching. We talk about they switch in the same direction, they switch in opposite directions, or don't switch at all. That has an impact on the specific power consumption as well. So we're going to conclude the lecture by doing this particular example question. The homework is going to be TGOs 4.16 through 4.22, and example questions 4.4 through 4.8. I'm sorry, 4.9. And so this is a good type of question because now we're starting to worry about, we have an input driving circuit, this 10x unit inverter, that it's driving a 2x unit inverter on the output. So now we have two engineers in two different groups. They've designed this inverter on the output that's 10x, and these other people say in order to meet these design constraints, it has to be 2x. So you as the engineer in the middle, you're the interconnect engineer, you have to tell them precisely, you have to design a wire that gets between them. So it's the same example from 1.8. So this is, we determined this in the last problem, 800 ohms. So we know that from this portion, we have a 10x unit inverter, right? And so a unit size NMOS transistor has a resistance of 10 kiloohms. Well, we know from our equation that the width is inversely proportional to resistance, right? So the first thing we're going to do, just from this particular problem, is we take it's 10 divided by 10 times kiloohms, because it's 10x unit, that becomes 1 kiloohm. The second portion is finding out the capacitance of the wire. So here we have the wire capacitance 0.2 femtofarads per micrometer, and we know that the length is a 1 millimeter wire, right? So we just multiply 2 femtofarads per micrometer times 1,000 micrometers, because that's the same thing as 1 millimeter. And that becomes 200 femtofarads. So now what we're doing is we're going to be having our, we take this value here of 200 femtofarads, and we know that it's a unit. If you recall, drawing our inverter, remember it's 4:2, we assume that to be our width-length ratio for inverters. So now we have 1 femtofarad of your unit size NMOS transistor times 2. And then, because we also have PMOS in there, it's going to be multiplied times 6. So our output capacitance of this unit 2 inverter is going to be 0.6 femtofarads. So first thing we do is we calculate the input resistance from our 10x inverter, right? And then we have the wire, which we calculated in the previous problem as 800 ohms, right? We've calculated the capacitance of the wire to be 1 millimeter and 2 femtofarads per micrometer. And therefore we get 200 femtofarads. So then what we're going to do in order to make this an Elmore delay model is we're actually going to split the capacitance in half, right? And we have it here and here. And then what we do is we have our input unit inverter, 1,000 ohms, 1 kiloohms, like we calculated. We have our wire, 800 ohms, 100 femtofarads and 100 femtofarads. We've now created our pi delay model. And then we have 0.6 femtofarads as our output inverter that we're driving. And then going back to 3.10, if you recall Elmore delay, we do R1C1 times R1 plus R2 times C2, and so forth. So to conclude, the actual solution is going to be 1 kiloohm times 100 femtofarads, because that is R1C1. And then we have 100 plus 800, because that's 1,000 plus 800 is R1 plus R2 C2. And then we're multiplying. Remember, these are in parallel. When capacitors are in parallel, you add them. So then you take these two capacitances, it becomes 100 femtofarads plus 0.6 femtofarads. So this becomes C2 that we multiply for our Elmore delay. And therefore, we're able to calculate the delay of the wire as 181 picoseconds. So now you know if we require a 1 millimeter wire for this given technology file, that's how long it's going to go from one cell to another cell. Does that meet the engineer's constraints? That's what you send back to them, and then they have to redesign if it doesn't. So does anybody have any questions on this before we conclude? All right. In this case, let me conclude, but there's a couple of you I need you to stay for a second.